From the Library of Congress in Washington, D.C.
Good morning. I'm Stephanie Marcus from the Science, Technology, and Business Division, and we host this lecture series with NASA Goddard, 12 years now, so it's really awesome. We've had some wonderful programs, and you're welcome to catch the old ones on our website. We have them all up there, and they are quite a range of topics. We try to do both space sciences and earth sciences, and sometimes we have a harder time getting the earth science people, so we had our hydrology person recently, and today we have our atmosphere person. And I think all of us get very upset if GPS isn't working or our computers or whatever. It depends on satellites and things where the weather in the upper atmosphere can really give us a hard time. So today we're going to hear about that. NASA has 2 new missions to study the ionosphere, upper atmosphere. And we're very lucky today to have Dr. Sarah Jones from Goddard speak to us. I'm not going to try to say what she's going to talk about because I have trouble understanding it. I thought I knew the air and space and all that, but there's a lot more to it. Dr. Jones is from Vermont, and she did her physics studies at Dartmouth. I see my former supervisor, Connie, is here. She's from New Hampshire. So she was really wanting to hear this. And also she got her PhD in physics from the University of New Hampshire. So I'm not going to say anything more. Let's hear about up there. Thank you.
Thanks very much, Stephanie, and thanks for inviting me here at the Library of Congress. I think this is an awesome series of lectures here. At NASA, we get really excited to come out and tell people about the great work that we're doing. At least we think it's great, and hopefully you will too. So today we're going to talk about the science of the upper atmosphere, by which I mean essentially the boundary between Earth and space. And so the atmosphere that we breathe here below thins out and kind of goes out into the vastness of space. And we're going to talk about this region where the particles are getting really thin, and some of them are charged. Stephanie mentioned the ionosphere. And this is a region that is going to be studied by 2 new NASA missions called GOLD and ICON. So NASA divides its science into 4 different categories. There's a lot of overlap between them. There's astrophysics, earth science, planetary science, and heliophysics, where I work, which is basically a study of the sun itself and then the effects of the sun on everything else, the Earth, the rest of the solar system. And so we're studying, in my group, the upper atmosphere and the effects of the sun on the atmosphere, which can be considered space weather. Now in heliophysics, we have a whole fleet of missions studying different pieces of the scientific puzzle, all throughout what's called the heliosphere, which is this region of the universe that's affected directly by the sun. We have the Voyager satellites that are basically at that very boundary, the edge of the sun's influence over the universe. And it's color-coded, where the orange missions are missions that are in implementation, which means they've either just launched and they're going through their commissioning phase, or they're going to launch soon. And so I wanted to pause here and give a shout out to the Parker Solar Probe, which here is called Solar Probe Plus. It's been renamed after Eugene Parker, who's a famous solar physicist. And some of you may have got this handout, which NASA is calling Solar Pizza. And it tells you about how Parker Solar Probe is going to be the mission that comes closer to the sun than ever before, basically touching the sun. So if you think about the sun being, let's say if it was 75 feet away from the Earth, Parker Solar Probe would be 3 feet away from the sun. It's really close to the sun, and it's about 2,500 degrees Fahrenheit, where it will be coming closest to the sun. And so this is a mission that's been dreamed about for decades, and we haven't been able to do it because that's really hot, and the satellite would have melted. But by now, engineering technology has come to the point where materials could be developed to shield that spacecraft so that it won't be destroyed. So that launches at the end of July, and my colleague Dr. Alex Young will be here in December to talk to you all about Parker Solar Probe. Today, we're going to talk about GOLD and ICON. GOLD is a mission that consists of a camera that's called a hosted payload because it's actually riding on a satellite that is not a government satellite. It's owned by a commercial company. And so we're renting a space and a downlink for data from this satellite. It's something new that NASA hasn't really done before, and it's a way to get your instruments into space and spend less money doing it, especially if you're going to a place like geostationary orbit, where GOLD had to go to make its measurements. So GOLD launched in January 24th of this year. The satellite is operated by SES Government Solutions. It's called SES-14. You can look it up on the internet if you'd like more information. And since then, the satellite has been slowly making its way up to what we call geostationary orbit, which is a location 22,000 miles above the Earth. And it will park there and sit there while the GOLD camera looks down at the Earth and takes pictures of what's going on below. This mission is led by University of Central Florida, and the principal investigator is Dr. Richard Eastis at the Laboratory for Atmospheric and Space Physics in Colorado. The other new mission to study the upper atmosphere is called ICON, Ionospheric Connection Explorer, and it launches in 1 week, next Thursday. And it's going to launch into low Earth orbit, which is the type of orbit that the International Space Station is in. So we'll be flying directly through this region of the upper atmosphere that we'll be talking about today. And it's going to study, essentially, its primary mission is to study how this region changes, this upper atmosphere changes in response to weather that we're experiencing down below. So this is a picture of the atmosphere. This is the stratosphere, right? This is where airplanes fly and where we have clouds. And then it fades out into the upper atmosphere that I'm talking about. And the region we're talking about today starts about 60 miles above us and then extends outward into space. So it's essentially the boundary between Earth and space. And you can think of the gas up here as just an extension of the air that we breathe below. It consists of oxygen, nitrogen, different types of gas. It's much thinner than it is here below. Think of going up to Mount Everest. The air gets pretty thin, right? At 60 miles, it's a whole lot thinner. And it moves, it has temperature. The gas has temperature and responds to pressure. And there's a wind up there, just like there is down here below. And so we see changes on long-term scales, weeks and months, which are like climate-type changes down here. And we also see changes on the order of hours or days, more like the weather patterns that we see down here below. Now, most of the gas up there is like the air that we breathe below. However, when the sunlight comes down and bombards the atmosphere, some of that neutral gas gets ripped apart into electrons and ions, and it becomes electrically charged. And so these ions, this small population of ions, is appropriately named the ionosphere. And the ionosphere and the neutral upper atmosphere are in the same region of space, this 60-ish miles above our heads, interacting with each other. And this breaking apart of the gas that's up there is one of the ways actually that the atmosphere protects us from getting too much UV light. So I wanted to show a video, an animation that was created by NASA to take us on a tour of the ionosphere.
Longing for more space, open skies, and exotic travel? Then look up, about 30 to 600 miles straight up, at the ionosphere, Earth's interface to space. Nestled far above the clouds but below outer space, this little understood destination invites you to explore its many features. Experience both the weather from Earth and the weather from space. Marvel at the ballet of radio waves and navigation signals, like GPS, leaping through this particle paradise. Sit back, relax, and take in the aurora, some satellites, and the International Space Station as they sail by. And you'll want your camera handy for one of the region's signature features, bright and colorful air glow. This daily show is made possible by the ionosphere's own swarming charged particles, because that's what the ionosphere is. It's all charged particles. During the day, enjoy the sea of particles, freshly energized by the sun. As the sun sets, this particle party relaxes and the air glow thins. Our quieter nightlife lets you gaze into clearer skies. The ionosphere is in constant motion, an amazing effect of space weather. Don't miss when solar storms rain down. The storm separates the particles even more, making this colorful region delightfully more dense in some places and stunningly sparse in others. And don't forget about storms from Earth below. Your weather from back home also stirs up this one-of-a-kind destination. Experience the unique beauty of every season, as changes in Earth's atmosphere, daily and annually, can create pressure waves, changing the ionosphere's shape and density. Venture to the equator, where our particles are packed in lush and thick. Cruise along a magnetic field line and see how the ionosphere's charged material also interacts with Earth's own magnetic field. Don't miss the superhighway of particles zipping out to space and back down to the planet. This unpredictable parade of charged particles can help you unplug and unwind. This is because the crowd of particles can garble the radio and satellite communications from home. The ionosphere welcomes you to discover more about this little-known region. After all, once you've explored this interface to space, who knows how much farther you'll be able to go.
So you saw in the video a little bit about how dynamic the ionosphere is. Because those particles are charged, they respond directly to magnetic and electric fields that are in the atmosphere and are moved around by them. And so you can get changes in the very shape of the ionosphere on a timescale of hours, and then you have longer-term changes like annual changes that were mentioned in the video. Now, the ionosphere is also the region where radio waves have to propagate through from our satellites to the ground for things like GPS. And we use it for other purposes as well. For example, when you're doing long-range communications from the ground, your AM radio station can send your signals up and actually bounce them off of the ionosphere to send the signal further than it would have gone otherwise. But when we get dynamic space weather, as it's called, when the radiation from the sun is changing, it's becoming more intense, there are things called storms happening, there can be structures in the ionosphere that can then garble the signals. Oh, I'm sorry. We don't need to say that again. And so the ionosphere can actually cause problems with long-range communications via radio waves, and it can also garble some signals from satellites, for example GPS, and then that can cause usually very small errors in GPS locations, which are important more for technologies that are on the horizon, like self-driving cars. But also, GPS is being used for some creative applications like sending out plow trucks unmanned so that they can clear ice and snow off of dangerous roads, or also for agricultural purposes so that you can have unmanned vehicles that are gathering crops. And so this is important for those types of applications. In addition to that, the charging of the atmosphere has effects on power lines down below. It causes what's called geomagnetically induced currents, which usually aren't a problem, but in rare cases can actually do some damage to transformers. And so power companies are really interested in learning about this process so that they can better protect their assets and prevent problems. So these are some of the reasons why it's important to understand the ionosphere. It's also important to understand the neutral part of the atmosphere. Remember, that's the bulk of the particles. And your satellites are plowing through these particles as they move through low Earth orbit, like ICON will, like the International Space Station does. And if you think about driving a car, right, ideally you want a very aerodynamic design for your car, because whether you can see it or not, you're driving through the air, and you want it to be deflected around your car. If you have a boxy car, you're going to use more gas. It's going to pull back on your car. Well, the same thing happens with satellites in space. The air is much thinner, but it still pulls on the satellite. And what that does to a satellite is over time the satellite actually loses a little bit of altitude steadily, and you either have to use some sort of active propulsion to bump it back up, like they do on the International Space Station, or eventually it gets to a low enough altitude where it actually re-enters the Earth's atmosphere and burns up. Most of it burns up. And there was a recent example, I don't know if any of you saw, of a Chinese space station that was re-entering the Earth's atmosphere. Most of it did burn up, and then pieces of it fell into the Pacific Ocean. But understanding when and where these satellites are going to go requires knowing the density of the gas up in the upper atmosphere, how much is there, what is the composition of the gas. And there was a well-publicized event in 1979 when Skylab, which was the American space station, re-entered much earlier than had originally been predicted. It was predicted before it happened. The engineers were updating their predictions over time, but it was much earlier than their initial prediction, because during the time that Skylab was up, the sun was actually putting out a lot more radiation than anyone had expected. And when that happens, the atmosphere receives all this energy and gets heated, and the particles actually expand. And so you get gas coming from down below. Now it's up at a higher altitude. Now you have a lot more gas that you're having to move the satellite through, and it loses orbit faster. And so, I don't know if anyone knows this, but as I was reading this article from CBS News, I found out that when Skylab did come down, pieces of it came down in Australia. The Australian government fined the US 400 Australian dollars for littering. And apparently we still haven't paid it, but okay. And so this is one important reason for just knowing how much gas is there, and when is it going to be more dense than it was before? How is this region responding to the sun's radiation, which then also requires a better understanding of what the sun is putting out, which is why we need missions like Parker. Another reason, though, is that we're not just tracking satellites. At this point, there's a lot of debris orbiting in space. One example is a problem that happened in 2009. 2 satellites crashed into each other and smashed into little pieces. And there was a bit of a concern for a while. Engineers went and rushed to make the calculations to see if there was a chance that the debris would come near the International Space Station. Because when debris strikes the space station or a satellite, it can do damage, or in that case even endanger the lives of the astronauts. And fortunately in this case it was okay. But making those predictions is really dependent on knowing the shape and the density of the gas in that upper atmosphere. And so we really do need to know both how the ionosphere works and how the neutral atmosphere works, and how they push on and change each other, so that we can understand what we need to know for our technologies. And one way that we can measure what's going on up there is to measure actually the glow that comes from these particles. They would be invisible, except there's a process called air glow, which makes it so that we can take pictures of the shape of the upper atmosphere, pictures of the shape of the boundary between Earth and space. And I have another video for you, last video, fortunately or unfortunately. And it's going to talk to you a little bit more about air glow.
The night sky is never truly dark. If you removed light pollution, the moon, stars, and galaxies, there would still be a very faint, colourful glow. That's air glow. With cameras, you can photograph it only on the darkest of nights. It's about 1/10 as bright as the combined light of all the stars. From above, it forms a luminous bubble encapsulating Earth. Appearing right at the interface to space, air glow holds clues to how our atmosphere affects weather in space, and how space weather affects humans on Earth. The bands of light span 60 to 400 miles above Earth's surface. In the uppermost boundary of the atmosphere is the ionosphere. This is where our GPS signals and astronauts travel. What makes this region complicated is that it's constantly changing. It reacts to both energy emanating from the sun and weather near Earth's surface. And as the ionosphere fluctuates, so can conditions in near-Earth space where the space station lies. But spotting changes in the ionosphere is a lot like trying to watch the wind. You need a marker of some kind to see the invisible particles move past. And for that, we have air glow.
So you just saw some pictures of air glow. You can see how it looks pretty structured sometimes. In addition to breaking apart neutral gas in the atmosphere, when sunlight hits the atmosphere, it also causes the ions of the ionosphere as well as the neutral gas to give off light. It glows in a variety of different colors, all across the spectrum of light from near infrared through visible light up into the ultraviolet, which is light that we can't see with our human eyes. And it's a really useful tool for us in studying this region because actually by measuring the light that's coming off of the atmosphere, you can determine to some extent the composition of the atmosphere because different types of gas, for example oxygen and nitrogen, will give off different colors of air glow. Also, in terms of measuring density and temperature, you can calculate that from measurements of how bright the air glow is. And you can even measure the motion of the particles from Doppler shifts in the light that you're measuring. So it's an extremely powerful tool for understanding this region. And this region, this transition between the Earth's atmosphere and space, it's really interesting because you've got these ionized particles moving in response to magnetic and electric fields, and then you've got the ions and the neutrals both moving in response to pressure gradients and temperature differences, much like the weather fronts that we have here down in the lower atmosphere. And so the neutral gas, responding mostly to the pressure and temperature, has itself a temperature of about 1,000 degrees Fahrenheit. It's pretty hot. The ions, actually, the ionosphere has a temperature that's a bit hotter than that. And if we could be transported and we could take a trip up to the ionosphere, we would actually feel a really strange sensation of having two winds at once, two different temperatures, two different directions, one denser than the other. It's trying to restart again. Sorry.
But not.
Okay. All right. So, for a long time, scientists thought that this upper atmosphere responded primarily to what's coming at us from the sun, and that was pretty much the only impact. And it certainly does have an impact when extreme ultraviolet light comes from the sun into the atmosphere. It heats up different parts of the atmosphere, in particular the stratosphere down below, which can then cause what are called atmospheric tides in the air, similar to the tides that we have in the ocean water. And so it's an effect coming from below, but it's indirectly caused by the sun because it's a result of the heating from the sun's light coming down. But in addition to those types of effects which cause different large-scale features in the ionosphere, the sun also gives off a steady stream of radiation and magnetic field called the solar wind, and sometimes can give off more of a burst of radiation. For example, when we have coronal mass ejections. Has anyone heard of those? The coronal mass ejection is when a sun essentially spits off a piece of itself and it goes hurtling outward, sometimes toward the Earth. And it contains solar plasma and magnetic fields that then interact with the Earth's magnetic field and the Earth's upper atmosphere. And this causes effects which we call space weather, and some of them are storms, typically referred to as geomagnetic storms, and they can cause large-scale, global-scale heating of the atmosphere, which will again then lift those particles to higher altitudes where they will more likely interact with satellites in low Earth orbit. And so for a long time, scientists thought this was pretty much the complete picture. But recently, in addition to the space weather that you get coming from the sun, there's been a growing body of evidence that shows that it seems like certain weather events from below are actually showing up in the upper atmosphere. Now this is a picture of air glow where you see the whole half of the Earth in air glow taken from the moon. In 1972, the Apollo 16 mission had a camera on the moon where they could image the Earth in the air glow. I think it looks kind of like a mouse. And so the bright half there is the half of the Earth that's getting hit directly by sunlight, and so the air glow is the brightest there. That tail of the mouse at the bottom is actually the auroral oval where you're getting the northern lights. And there would be one, and the southern lights, so there should be one on both sides. You can't see the other one because it's swamped by the air glow emissions. But on the night side, the mouse has some little arms coming out. This is a feature that was discovered in the 40s by a scientist named Appleton. It's called the Appleton anomaly, although it's not so much an anomaly now because it's been explained. And without getting into it, because it's kind of complicated, I just wanted to point out that the mouse's arms look pretty smooth. But recently we've had cameras with higher resolution that have gone through and measured the Earth in the same way. For example, the IMAGE satellite, and we've been able to build up pictures like this, where those arms of the mouse are actually bands that go all the way around the Earth, and they're not smooth like scientists thought. There's actually a sort of bead-type structure there where you have bright spots along the arcs. And this is an image that's in a paper by Dr. Thomas Immel, who's the PI, the principal investigator of the ICON mission. He's leading that mission. And he shows evidence that these bright spots correspond to weather that's happening below in the tropics. And so this and other evidence that's similar was part of the motivation for the ICON mission. ICON is designed to study really this brand new area of scientific research, right? It's like for a long time scientists have been saying, well, just ignore what's happening below because it doesn't affect anything. And now there's evidence saying, hang on, you shouldn't have ignored that. So NASA's going back, and we're not going to ignore that anymore. We're going to start measuring what's happening in the upper atmosphere in response to the weather below. So ICON has 4 instruments. So this satellite will be orbiting in low Earth orbit, actually flying through this air glow that you're seeing. And on the horizon, it's going to take pictures of the air glow in infrared, visible light, and far ultraviolet light. And from those measurements, it can get the temperature. It can get a measure of the winds, where the neutral particles are moving, and it can get a measure of the composition and how many ions are there. And in addition, they have another instrument that's called an in situ instrument. It takes measurements right there locally. It's an ion velocity meter that gathers up the particles and measures them to determine the drift of the ions. So you're getting that second wind. You're measuring both the wind of the neutral particles and the ionized particles. And it's also giving information about the electric fields in that area. Some additional evidence that the weather below is actually affecting the upper atmosphere is a computer simulation done by Astrid Maute, who's also a part of the ICON mission, where she showed that during El Nino, when the ocean water is warmer, it causes more water vapor to be released, and that sets off a chain reaction that can push the lower border of the ionosphere upwards and actually change the shape of that boundary. And again, that moves the particles up to a higher altitude. And so, in her computer simulation, this plot on the right shows the density of the ionosphere during one of these events. And you have longitude on the x-axis and latitude on the y-axis. And you can see that because particles were lifted up in certain areas, the ionosphere is more dense there. Particles from below came up and increased the density. So that's one way that El Nino could affect the upper atmosphere, and now ICON has to go and see if they can measure that. They'll be flying right through regions like this that are expected to have higher density. But one of the coolest things that we want to measure is gravity waves. Not to be confused with gravitational waves, which are the warps in space-time that won the Nobel Prize in 2017, but still interesting nonetheless. These are buoyancy waves. If you think of water flowing over a rock, you get ripples in the water. The same thing happens with air. Air flowing over mountain ranges will be rippled. And also, in this case, this is a computer simulation of what the upper atmosphere would look like after a tsunami. The tsunami is a large storm, and the cyclone actually sets up this ripple structure in the air. And so this is the type of measurement that ICON and GOLD will be making. ICON will be flying through those ripples, right? But GOLD will be sitting 22,000 miles above, looking down, getting this whole big picture. And so when ICON says, well, we've seen some ripples, but we have no idea where they're from, GOLD can look and say, well, we see there's a big storm near you, and that's where they're coming from. And it gives us the complete picture of what's going on. So you can think of GOLD as like your typical weather satellite, only it's looking at the upper atmosphere instead of the lower atmosphere. And you can think of ICON as sort of the hurricane chasers going into the eye of the storm. And so as I mentioned, GOLD launched in January. It's going to give us these images much faster than we've ever had before. Once every half hour, which might seem kind of slow compared to what we're used to. But what we've had in the past was more like one per several hours, or even one per day, or several days. So this will allow us to have enough resolution to measure what would be considered weather effects rather than long-term climate type effects like we measured in the past. So this video just shows the viewing geometries of the GOLD and ICON missions. GOLD is actually hovering over a fixed location, so it's rotating with the Earth. It's hovering over the mouth of the Amazon River. And ICON is cutting through in the atmosphere below. It whips around at a rate of about 1 orbit per 90 minutes, an hour and a half. And GOLD is a camera that actually has a slit field of view. So it takes a picture, then it moves over a little bit, takes another picture, and so on across the northern hemisphere. And then you'll see it go back across the southern hemisphere, and it builds up a complete, essentially mosaic image of what's going on below. And those little triangles coming out from ICON, those are the fields of view of the different airglow cameras that they have on board. And once GOLD gets done scanning across the Earth, it actually goes back and scans the horizon, which is where ICON is looking from down below. It gives a different type of science. And so this color scale here is what the ionosphere will look like when it's being measured. GOLD actually will be measuring light from the neutral particles, so it will look a little bit different, but it also changes from day to day. And so the air glow gives you a sort of modeled look that corresponds to the shape of the atmosphere, the density, what kind of particles are there, and it allows you to get most of the information that you would need for any sort of computer simulation that you're using. Other information will come from missions like Parker Solar Probe, where you're getting information about what's coming from the sun. And this will help us move toward first being able to understand what's going on now, right? That's what we call nowcasting. And then over time being able to start forecasting and saying, look, this is what's happening at the sun, and so we can expect this sort of effect in the atmosphere, which might have this sort of effect on our technologies. And so that's where we're heading. Golden Icon won't get us all the way there. It's like the very beginning of forecasting weather down here on Earth. But they're a big step in the right direction that will help us understand and try to tease out the different effects of what's happening at the sun versus what's coming up from down below, tsunamis, El Nino, other weather patterns like that. And so, before I go, I wanted to invite you to watch the ICON launch on NASA TV. And so this is a picture over here of the fairing that ICON will go into. They just did their mission readiness review, I saw on the NASA blog yesterday. So they're moving forward toward launch. It launches next Thursday, which is June 14th, and it will be, the coverage will start at 9:45 a.m. Eastern Time. The launch will more likely be around 10 a.m. And that you can watch it on NASA TV, on your TV station, or you can watch it streaming on the internet. And so we're very excited for this, and I just want to thank you all again for coming and listening.
Thank you so much. I guess one of these days we'll have the space weather girl, who's also giving that forecast along with the Earth weather girl. We'll take questions now, and Dr. Jones will repeat them so everyone can hear them.
You mentioned in the ionosphere that it appeared there were two winds potentially combining. Have they shown any indication of some type of whirlpool configuration that we see in rivers occurring in the ionosphere?
So the question was about the two different winds that are happening in the upper atmosphere, the ion wind and the neutral wind, and whether or not we see whirlpool type effects. Actually, there are all kinds of really interesting effects, not exactly the same, but happening in the upper atmosphere. For example, those two arms of the mouse, the bands that are around the Earth, they're really symmetrical around the Earth's magnetic equator. And they actually are caused by what's called a fountain effect, which occurs because of the Earth's magnetic and electric fields pulling on those ions. And it causes them to move upward and then outward and down, kind of like a fountain. And that's what produces the light in those two bands. There are also other patterns that I'm not very familiar with, but one called the winter polar vortex, which also moves air from the polar regions down toward the equator. So yeah, there are a lot of similarities like that too.
What are the effects of the El Nino thickening of the ionosphere on Earth?
So the thickening of the ionosphere, it could potentially cause effects like small changes in the accuracy of GPS or issues for long-range communications. Ultimately, the big effect, I think, would be on satellites that happen to be in low Earth orbit. If the densities get high enough, it can cause charging on the spacecraft, which I don't think would damage it, but could affect instruments and the measurements on those satellites. I think that would be the main effect in that case.
What is the relationship, if there is one, between air glow and the aurora borealis?
Sure, thank you. And I forgot to repeat your question. You were asking about what would the effect of the El Nino density in the ionosphere have down here on Earth. But your question was, how are the aurora and the air glow related? Is that right? Okay. Yeah, they are related actually because they're both very similar chemical processes. So the aurora happens when the sun is giving off this steady solar wind and magnetic field, which then impacts on the Earth. Some of those particles leak into the Earth's magnetic field area and kind of get stuck there and hang out there. And then ionospheric particles also kind of leak upward into that region. And then during some geomagnetic events like coronal mass ejections, they can get accelerated in a way that causes them to cruise down the field lines, kind of like in that ionosphere video. That's why you get the aurora in a ring, because it's particles that are traveling down field lines from a region where they got accelerated. But what causes the light is those particles coming down, they impact the atmosphere, knock electrons off of the particles there. That causes them sometimes to give off light immediately. Other times, you get other light also from when the particles recombine, and certain chemical interactions give off certain types of light. So that's how it works in the aurora. In the air glow, it's almost the same thing, it's just sunlight causing it to happen. And so you also get excitation, they call it, where you get this immediate release of light. And then you also get recombination, especially at night when you're not getting bombarded with sunlight anymore. Those electrons and ions kind of find their way back to each other. And some of them, when they recombine, will give off light in a variety of different colors. So it's very similar.
I think you mentioned the gold satellite was a hosted payload on another satellite. What's the other satellite for, and how do you build it so that one doesn't affect the other, or do they affect each other?
Yeah, that's a great question. It's about the gold mission being a hosted payload and how you avoid the one mission affecting the other and what the primary mission is for. I actually don't know what SES Government Solutions is using SES-14 for. I don't think it's classified or anything. I'm just not familiar with it. I think it could be a TV satellite, but that's speculation. But we did go through a lot of measures working with SES, which is the parent company, and SES Government Solutions, all along, actually from even the proposal stage before the mission was selected. The gold team was working with SES, talking to them about these exact things and how do we avoid affecting each other adversely. They wouldn't want us if we were going to affect them, and NASA wouldn't let us launch if our data were going to be affected. And so it was just this long-term collaboration, essentially, which worked out quite well.
The surface of the Earth is moving roughly about 1,000 miles per hour. Is there a defining point where the atmosphere relative to space slows to zero, or so many feet per minute or miles per hour, and then where it's, space is zero?
Yeah, so essentially getting out of the Earth's atmosphere depends on reaching an escape velocity, right? So that your velocity is actually faster than gravity can pull you down toward the Earth, essentially, to keep you up out of there. In terms of, and the question was about the atmosphere as it becomes space, and that boundary there. Is there a defining point where the particles stop moving with the Earth, essentially? Yeah, I think that the answer would be that the particles fall off gradually, and where the point is that becomes space, I think, is something that we haven't really measured. I'm not sure if there probably are models that would say, but that actually would be dependent a little bit on that expansion of the atmosphere due to the energy coming from the sun.
And follow-up, is there any stripping of our atmosphere, or was there ever at any point? I know with ozone, the hole in the ozone at some point, but is there stripping because of that movement?
Yeah, the question is there a sort of stripping effect of the atmosphere? And I think that's a really great and interesting question, because I think on other planets in our solar system, that's the understanding, right? Is that they may have had atmospheres in the past that were stripped away. This is not my area of expertise at all, but I am really interested in it. And I think that the idea is that certain types of gas could have been stripped away in the past, but you'd have to ask someone more expert than me. But thank you.
On the
slide up there. It says the satellite and the rocket on June 6th were in California, and on June 14th they're going to be out in the Pacific. How do you get the rocket out there?
Yeah, and then thank you for pointing this out because I poorly made this slide actually. This picture is from May 22nd, 2018. At that point, the satellite and the rocket were all in California. Yesterday they did their mission readiness review, and I don't know when it happens, to be honest, but I do know that what happens is that they take the rocket and the satellite and everything all put together, they ferry it out to the Marshall Islands shortly before launch on June 14th.
On a ship?
I think so, yeah. Mm-hmm.
I was also interested in that, in the type of launch where it's going to be an airplane with the rocket and the satellite. Now, why do they use the airplane? Normally they would just use the rocket. Right?
That's right. I think, and again, it's not my expertise on why ICON is being launched on this Pegasus rocket, which launches from an airplane. They actually take off with the airplane first. But I believe it's because you need less thrust and propulsion once you're already in the air above the densest part of the atmosphere. And so that makes it easier to get it up into orbit.
That should be interesting.
What's the benefit from launching it all the way out in the Pacific versus Vandenberg or anywhere else?
I know it was something that had to be discussed. Why would you choose to launch from Marshall Islands instead of somewhere like Vandenberg or Kennedy? I believe that the reason was because the Marshall Islands gave them the inclination that they wanted for the orbit. So it's something like a 20 or 22 degree inclination orbit, which allows it to get up around the tropics and also measure near the equator. I think that was the reason.
Wasn't it fairly recently that the charged particles in the air globe were photographed, like within the past 20 years or something?
So the question is, how long has it been since we started measuring the charged particles in the air globe?
Yeah, I just remember seeing like a photograph. It was like a discovery and everybody was excited about it.
Oh, yeah, I think I know what you mean. One of the satellites that was able to measure the aurora, both regions and all of the air glow at once, it was the first time it was done very recently. I'm sorry, I don't remember what mission that was, but in terms of just measuring the air glow, it's actually been something that's been done since the beginning of this research field, also measuring the aurora. And it's an interesting question because we can use the upper atmosphere as a real laboratory for chemistry. Actually, there were chemical emissions in the aurora and air glow that had never been seen on Earth. And so there were big debates about what is this? What is the light coming from? We know it's coming from a chemical reaction between the particles, but there were even speculations about new elements in the periodic table that might give off this kind of light. And the reason was because some of these lines come from metastable states, which, at least at that time, and the level of vacuum that they could achieve in their laboratory experiments, they would never see in the lab. So the red line that happens in the aurora and the air glow, the particle receives the energy and just kind of is metastable, so it hangs out for like an entire minute before giving off light. And unless you're at a really low density, before that minute is up, you're going to get hit by some other particle, and it's going to lose energy that way instead of giving off the red light. So, yeah, it's been this really great way of studying basic chemistry.
Have we exhausted the questions? Well, thank you all for coming, and we'll see you in September. We have a little hiatus before our next lecture, so thanks again for coming.
Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.